Hey everyone, today we have another problem with you to go over. We are going to be doing a torsional angle twist. It says in the problem statement, the hollow shaft shown is made from 2014 T6 aluminum with a shear modulus of 4,000 kips per square inch and a modulus of elasticity of 10,600 kips per square inch. The inner and outer diameters are 5 inches and 8 inches, respectively. And here we have a detail of what actually is happening. We have the shaft right here that's fixed at the left end, and then we have a cross section that shows us the inner diameter cross section view of it. So if you're looking at the side view, now it's asking if the design is governed by the maximum angle of twist, which is limited to 2 degrees, the maximum torque the shaft can support is most nearly. Now the key right here is units. We can see here that we have some units that are in feet kips. So with that said, we have to make sure that our final answer, the units make sense. Now I'm going to be referencing both the CERM 15th edition and the FE Handbook 10.0 edition, just to give you both backgrounds if you're studying for the PE or for the FE. Now the CERM 15th edition, for in this case, it's a hollow shaft that's stated in the first sentence or the first few words of the sentence. And right here, which actually, let's try to see what we're trying to find, I suppose. We're trying to find the maximum torque the shaft can support. So because we're trying to find the maximum torque the shaft can support, in the CERM 15th edition, I can see this equation right here where I have my angle of twist equals TL over JG, and that's equation 45.54. Now in regards to the FE, and I'll do that in a different color, and I'll do FE 10.0, they have it a little different. For torsional strain, it's the same concept, but they have it a little differently. They have it as phi equals TL over JG. Regardless, this phi or this gamma, the units are in radians. So that's something you have to be careful of, because they give us the maximum angle of twist permitted or limited to is 2 degrees. So we have to make sure that even though they give us this 2 degrees, we have to convert that to radians. So let's see what else we can have. So we gotta find, so let's go ahead and actually write up here what we are given. So we have our gamma, which is 2 degrees. Now I'm gonna go ahead and convert that, times it by pi radians. There is 180 degrees. And when I do that, I get 0.035 radians. Okay, so we got one of them. Now let's look at our L. So we have L is 10 feet. That's good because our answer wants to be, we want it to be in feet kips, as we can see in these units. Let's look at our J now. Our J is our polar moment of inertia. So polar moment of inertia is going to be a little different since we have an outer radius and an inner radius. And in accordance with the hollow shaft, the equation for the polar moment of inertia for a hollow shaft goes as follows: as pi over 2 times it by radius outer to the fourth minus radius inner to the fourth. Now you can try to do the diameter, but I'm just gonna try to keep it as radius because I see it's gonna be easier. I try not to, if an equation is given to me in a specific unit, a specific value, saying this is radius versus this is diameter, then I try to keep it how it is, so I don't manipulate the equation any more than it has to be. But you can do it in with diameter as well. So the diameter we have is, we have diameter outer which is 8 inches, diameter inner, which is 5 inches. Or I can say my radius outer is 4 inches, my radius inner is 2.5 inches. So that's what I have here now. G is my shear modulus, which in this case is 4,000 kits per inch square. So let's go ahead and find our J real quick. So J equals pi over 2 times it by 4, and I'll put it in this. Actually, let me go back. Times it by 4 inches to the fourth minus the inner, which is 2.5 inches raised to the fourth. And when I do that, I get a value of 340.8 inches to the fourth. Now I can see something, and I'll go ahead and bring these down here. So I can see, and I apologize, it's clustered, that my angle of twist is 0.035 radians. Okay, no problem. I have my J is 340.8 inches to the fourth. Okay. I have my shear modulus is 4,000 kits per inch squared. Okay. But then I have my L, or my length, is 10 feet. Now to make the units simple, again, instead of converting everything else like this inch to the fourth to feet to the fourth and all this, I'm just going to multiply this L by 12 inches per 1 foot and get 120 inches. Okay, so I'm going to use this equation right here, and I'm going to solve for what I actually want to solve for. So I'm going to say that gamma JG equals TL, therefore T equals gamma JG over L. Okay, so now I know I'm going to solve for. I'm going to plug some values in. So I know my torque, but actually before we do that, let's look at the units to see what units we're going to, if we do it like this, what units we're going to end up with, just to make sure that we're on the right track. So my gamma is in radians, which is a unitless value. My J is in inches to the fourth. My shear modulus is kips per square inch, and my length down here is in inches. So if I just do the quick symbolic math right here, then I'll get a few values. This will make it cancel out, and this will create this as a 2. So I'll have it as inch squared. Actually, and I'll make it a little different. Make it a lot simpler. Times inch times kips over inch. With that being said right there, I can cancel out 1 inch, and I get kips inch. However, I want kips feet, correct? So what I had to do then is, and I'll do it in black, times this by 12 inches, there's 1 foot, to get my answer in kip feet. So I'm going to have to remember this last part right here to divide it by 12 inches, or to multiply it by 1 foot over 12 inches. So let's go ahead and plug our values in. So we have T equals our radians, which is 0.035 radians. So here's our gamma. Then we have our polar moment of inertia of 340.8 inches to the fourth, which is our J, or polar moment of inertia. We have our G, which is our shear modulus of 4,000 kips per square inch. And then we have our length of 120 inches. Now when I do that right there, I get a value of 397.6 kip inches. But we said our answers aren't in kip inches, they're in kip feet or feet kips. So what that means is we have to multiply this guy right here times it by 1 foot. There's 12 inches. Therefore, my torque equals 33.1 kip feet. And with that being said, I know my answer is going to be C. Let me know if there was any part that didn't make sense, or if you need better clarification. I'm happy to help, and we're gonna try to do more videos of these series where we can knock out some FE and some PE problems. But let's do a quick overview of this, just a quick summary. They gave us some more information than we intended, than we needed, because they gave us this modulus of elasticity of 10,600 kips per inch squared. That wasn't even needed anywhere. We didn't have to use that. So you have to be careful and be aware, what are you looking for? And just ensure that you understand truly what you're trying to find, because we had a shear modulus, we have the angle of twist, which is limited to here, and they're asking for the maximum torque. So because they gave us that, I know that we have to use the angle of twist equation, which is TL over JG, and that gamma or that phi is in radians always. So be aware of that. That's going to be something that they will get you for if you use degrees. That will be an answer, and they will try to mark you off for that or where you miss it. So make the mistakes now. Don't make them on the test. Understand what's going on with the problem and go crush it. Thanks, guys.